the point is that this is the general form of the bond that exists between amino acids inside proteins. Now, if you take an amine and condense it with a carboxylic acid, this results. Well, wait a second. That means that if we're taking off an OH from this end and an H from that end, then what happens if you try to do it with, say, trimethylamine, or technically N-dimethylmethanoamine, methanamine? So, I mean, is this going to work? No, there's no hydrogens for this to displace. So, this only works for primary and secondary amines. So what does this require for the amine? Primary or secondary. What properties can be expected from an amide? Well, if it's a primary amide, then it has some capability of hydrogen bonding, which, by the way, is why secondary structures such as beta-pleated sheets and alpha helices are stable in proteins and can be used as structural elements. So, what happens though if you have, instead of a primary amine being used, you use a secondary amine? Well, there's not as much capability, not nearly as much, for hydrogen bonding. It's also much, much less polar overall. So what does that do? Well, first of all, we note that amide nitrogens are not. Unlike amines, they are not basic. Why? Well, oxygen is much more electronegative than nitrogen, which means that this can partially pull these two over here a little bit and these two over there a little bit. This also happens to mean that this whole bond is flat. That is very important when it comes to protein structure, for example. Now, if the chain length on either side get longer, well, it's pretty obvious that as the chain lengths grow longer, the alkyl traits will increase, the boiling points will approach the alkane, the corresponding alkane, or alkene, or alkyne, and, well, corresponding as in of similar molecular mass. That's very important, because corresponding does not necessarily mean of similar chain length. Why? Because we know that oxygen is 16.00, whereas CH2 is only about 14.03. Now, so as the chain length increases, the solubility in water decreases. And the solubility in organic solvents, i.e., say, alkanes, increases. Now, what else can we think of? Well, wait a second. If we know that using a secondary amine to start with gets you less polarization and more alkane-like characteristics than a primary amine, then what happens if we just use ammonia with a carboxylic acid? And thus this is also hydrogen. Well then, that's even more polar, which means that the characteristics are further away from alkane-like. Now when we're naming amides, it's like naming esters, but here instead of naming whatever's on the other side as a substituent on the deprotonated carboxylic acid, instead of that we name it as a substituent on the, well, amide. And how do we denote that it's an amide? Instead of ending in O8, we end in amide. Why is it that we only remove the little e at the end of, say, butane? It's because we want to make sure that it's still obvious that this could be an E or a Y even. So butanoic acid or butynoic acid can all be used to create a corresponding amide. So That's why we only, instead of removing the whole ane, we only remove the E at the end. Alright. N-methylbutanamide would be, well, okay, first of all, we start with butanamide, which is 1, 2, 3, 4. N-methyl. And that's it. You can choose to label the H here if you so wish. Most teachers will let you get away with not doing so, though. So, N-dimethylbutanamide. Well, that's still butane to begin with. And then N, 2 methyl groups. There. Now, reactions for amines and amides. If you have an alkyl halide, for example, CH3I, iodomethane. Well, if you take this and add it to ammonia, it tends to take the I and an H and become, well, how many H's do we have here? We know that this is going to be bonded to NH2, so clearly this has to be 3 still. So we see that this happens, plus HI, so hydroiodic acid. Now, why does this reaction stop here? The answer is, it doesn't. If you have more of this, then you can go on and go to, and then go on further and get trimethylamine. Yeah, okay, technically N-dimethylmethanamine, but most chemists still use trimethylamine just because it's so much faster. Okay, now, how do we prevent this from happening? How to stop? We add more ammonia. So if we have more ammonia, then it is unlikely that this particle will encounter one of these intermediates instead of just running into more ammonia and forming this first intermediate. So when you conduct an industrial reaction to manufacture, say this, so methanamine, you use a very large excess of ammonia. Now, amides are synthesized by carboxylic acid, so R, COOH plus N, R, and R. So, this ends up coming off. The mechanism will be discussed at a later point. Now, this comes off, and thus these two atoms are bonded together. Now, this can be hydrolyzed in acidic or basic conditions similar to esters. And this reproduces the carboxylic acid and the amine. In summary, amines can be seen as alkyl groups bonded to a nitrogen atom. Primary amines have one alkyl group attached to the nitrogen. Secondary amines have 2. And tertiary amines have 3. There are no quaternary amines, unlike, say, quaternary carbons, which do exist. Now, we could also see this as an amino group bonded to an alkane. When we name it as a substituent, we get, say, methylamino. So, N, and this is whatever else, N with methyl, or ethylamino, or propylamino, and butylamino, pentylamino, and so on. So, amines are named by adding the suffix amine to the root of the name. Now, this is almost as seemingly obvious as adding oic acid. Why did they insist on adding the acid? It's because, well, I guess they believed it was special enough that instead of just saying butanoic, they had to say butanoic acid. Well, as if they say so, then we will have to cooperate, because we currently cannot change the world ourselves. We must adapt to the world before we can change it. Hopefully we will all grow up to change the world. Now, the prefix N would indicate that a second or third, or, well, third is it. Because, well, first of all, even for carbon, third is it, because it has to have a main chain leading in. And, well, these are alkyl groups that are also attached to the nitrogen atom. What happens, though, when you have, say, multiple? Say something like this. Well, you choose one that you say is more important, and you name the other one as a substituent. Now, amides are formed when you react carboxylic acids with an amine that is not tertiary, so an amine that has a hydrogen it can give up to participate in this condensation reaction. Now, amides can be hydrolyzed to reform the amine and the carboxylic acid in either acidic or basic conditions. Obviously, if you do this in acidic conditions, the amine is going to come out as protonated. And if you do this in basic conditions, the carboxylic acid will come out as deprotonated. Now, what happens when you want to, say, extract an amide that you synthesized from some solvent? Well, if you don't want to break it down and then reform it, then, well, you basically have various methods, i.e. basically crystallization is about it. So crystallization using an ice bath. Now, an ice bath works by, of course, you have to let the solution cool to room temperature in the Erlenmeyer flask first before you put it into the ice bath, because you don't want the glass to crack. That would be bad. It would spill your stuff. So you put it in the ice bath, and that's going to be 0 degrees Celsius, because it's a mixture of ice and water, or slightly below 0 if there's some salt involved. Now, if you can break it down and then you want to reform it later, then you can use an extraction funnel. What is an extraction funnel? Well, an extraction funnel is a piece of lab equipment that looks like this. It's very useful if you synthesize something that is soluble in a different solvent from what you began with. So here there's a knob. And the general point of this is that you add a certain amount of a certain solvent, you add whatever your reaction medium was. So say you have water and ether, or water and tetrachloromethane, which is actually denser. Now, what do? Of course, you keep this sealed. You plug the top with a glass plug, glass stopper, and then you shake vigorously. Be careful to not hit anything by accident when shaking. I have seen this happen, and the results are not pretty. Now, you shake vigorously, you try to mix these up as best you can, and you will find that if, say, you're trying to extract a carotenoid from a water-based solution into one where it's much more soluble, i.e. an organic solvent, then by organic solvent we usually mean one that's nonpolar when you talk about it in a lab context. So when we extract that, you can sometimes see the color moving from one medium to the other. Now, you will, if what you're trying to extract into is heavier, then that's easy. What you do is you let it settle for a while, and then you drain the heavier fraction into a beaker. If that's what you're looking for, great. What you do then is, once this is almost done, you close it, you add more of that solvent, you extract some more, and you do another run. And I think you get the idea here. Then finally you take this and you go crystallize it using an ice bath. Now, if what you're trying to extract into is lighter, then that's a little bit more complicated. First, you let it run. A little bit of what you're trying to extract will exit into this. So there's going to be a little bit that you spilled, so to speak. And then you let what the medium you're working with, the particular solvent, run into another beaker. So a new beaker or a flask. And then you take the contents of your initial fraction that you want to keep on extracting from, you seal this up, you pour it back in, you add more of your second solvent. Now, I think you get where that is going. And then you take the fraction that you want to extract into, and then you crystallize. Alright. So be careful though that you make sure you choose solvents where the solvent doesn't turn solid before the water temperature. Thankfully, typical solvents stocked in labs do not have the problem of trying to extract, say, carotenoids from a block of solidified, well, fats, say butter. Now, amides are named with the alkyl groups of the amine as substituents on the nitrogen of the amide. What happens though if these substituents have themselves some substituents? Well, we might have two, first of all we use brackets, hydroxy and butyl. Now here this is always going to be hydroxy because when we name substituents, well, this is a sub-substituent, so to speak. This is not the main dictating term of this item. Because alcohols have lower priority than amides. N2-hydroxybutyl. And this could be, well, a lot of things. This could be, let's think about what we want to use for the carboxylic acid part. Ethanamide. So, two hydroxybutyl, butyl, and because that's 4, and 2 hydroxy. Well, 1 is the closest carbon to the nitrogen, so 2 is over here. Now, that's it for this section, and that's it for this chapter too. So we'll see each other again in chapter 2.